So we're moving along in our e-learning, and we've made it all the way to Unit 10, which is on gas laws. And so yesterday you kind of took a look at a little simulation to kind of introduce you to the three main variables of gases, which are pressure, temperature, and volume. And so what we're going to do today is kind of talk about those variables a little bit more, make sure you're good to go on your gas laws. And then we'll kind of practice actually working out some calculations with the different variables. And so again, just a reminder about our three main variables. We have volume, which is the amount of space that a gas typically, occupies. And typically it's going to be measured in liters. Then we have pressure, which is the force that the gas particles exert on their container. And so the idea is, if you think about kind of a box, and let's say it has some gas inside it, the more often the gas particles hit the walls of the box, the more pressure they will exert, all right? The more force. The less often they hit the walls of the box, the less the pressure will be, okay? And typically we have pressure either measured in what's called atmospheres or sometimes millimeters of mercury. And then finally we have temperature. And all temperature is just a measurement of how fast the particles are moving, or their kinetic energy, in other words. So the faster they're moving, the higher their kinetic energy, the higher the temperature. And in terms of gas laws, it's typically measured in Kelvin instead of degrees Celsius. And so just as a reminder, if you're given degrees Celsius, we add 273.15 degrees to convert it to Kelvin. All right, so if we take kind of these three laws and try to look at their relationships, they can be related by three different laws. And the role of a law is to simply describe what happens. So for example, a law might say, as the volume goes down, the pressure goes up. And that's Boyle's law. It relates pressure and volume. And what we found is that pressure and volume are inversely proportional. That means they go in opposite directions. If pressure goes up, volume goes down. What remained constant was the temperature, and the equation for Boyle's law is P1V1 equals P2V2. And then your graph kind of looks like a curve, again showing as your pressure was going up, your volume was coming down. Then you went on to learn about Charles's law, which relates volume and temperature. These we found to be directly proportional whenever you would measure just those two variables and hold the pressure constant. So when you're expressing kind of direct relationships in an equation, you typically end up dividing the variables. So it was V1 divided by T1 equals V2 divided by T2. And the graph was a straight line because as temperature went up, so did the volume. And then finally, we had Gay-Lussac's law, which related pressure and temperature. These were also directly proportional, meaning the higher your temperature, the greater your pressure will be. And that's because, again, with a high temperature, your molecules are moving really fast, so they're going to be bouncing off the walls of the container very frequently to generate that high pressure. What will be constant is the volume, and your equation is going to look very similar to Charles's law, whereas P1 over T1 equals P2 over T2. And again, what those little subscripts are going to stand for is the subscript 1 is going to stand for your initial or starting conditions. Then what we're going to do is make a change, and then we'll measure kind of the ending or the second conditions, and that's what the little 2 stands for. And then, of course, just like Charles's law, your Gay-Lussac's graph is directly proportional, so it should be a straight line as well. Okay. Now, it kind of seems like a lot, when you have all three of these laws to remember. And so what they've done to make it easier on us is they have combined them into kind of one big equation called the combined gas law, and that's in the top right-hand corner here. So this is the combined gas law that lets you take a look kind of at all three variables at once. Now I also kind of know a little trick that can help you use the combined gas law to kind of remember, which law is Boyle's, which law is Charles, and which law is Gay-Lussac's. So if you look at the combined gas law, it's, the same on both sides except for the 1s and the 2s. But if you write the first 3 letters of the alphabet, A, B, C, kind of across the top, if you let A stand for Gay-Lussac's law, the variables that kind of are diagonal to that A give you Gay-Lussac's law, pressure over temperature. If you let C stand for Charles's law and do the same thing diagonally, that gives you volume over temperature, which is the same thing as Charles's law. Then the B in the middle, if you take the 2 variables on top, pressure and volume, that gives you Boyle's law. So that's an easy kind of memory trick to help you remember, which law is which. All right. And so now what we're going to do is we're going to put these laws into action to help us calculate, what will happen to the pressure, volume, or temperature when we make changes to a gas. And if you'll put a big star or kind of highlight, this portion right here, that when we're working gas law problems, you always want to change the temperature to Kelvin. And again, to do that, you'll take your degrees Celsius and add 273.15. All right, so let's jump in and see what we can do. So we're actually going to kind of skip the I do and save that one till last. I kind of accidentally put the harder one at the beginning. So let's start with the we do and kind of work our way down, and then we'll come back to the I do at the end, and that should give you kind of all 4 examples of how you can use this particular combined gas law. So what we need to do first is figure out, which variables we're actually working with here. So I'm going to kind of write just the basic form of our ideal gas law, PV over T. And then let's kind of read our problem and see which of those variables we'll actually be using. So back to our we do here. It says if 2 liters of a gas is at 740 millimeters of mercury, what is its volume at 760 millimeters of mercury? So when they start off, they give us 2 liters of gas. Liters, I know, is a volume, so I know I'll be dealing with volume. Then they tell me I have 740 millimeters of mercury. And that is one of our pressure units. And as you work more of these problems, you'll become more familiar with which units kind of correspond to which variable. And so if I'm only dealing with pressure and volume, that must mean that the temperature is being held constant. So it won't be factored in to our solving of the problem. So what that means is this is a Boyle's law problem. So I'll write my equation, P1V1 equals P2V2. Now I'm going to come to the top and kind of make a list. That way I can keep track from the word problem of what specifically my variables are. All right, so pressure 1, they tell me I start with 2 liters of a gas. So that will be my starting volume. And then my starting pressure is 740 millimeters of mercury. Then they tell me my final pressure is 760 millimeters of mercury. And they're wanting me to solve for the new volume. Now, before you work a gas laws problem, it's always a good idea to predict what the answer will be before you actually start trying to solve it. So here we see a general trend that the pressure is increasing. Now, based on what I know about pressure and volume, if the pressure goes up, the volume should do the opposite and go down. So our prediction is going to say that the volume should go down. And so what we'll do is we'll solve the problem. And if our prediction, doesn't match, then that means that we may have made a mistake somewhere in either our setup or our calculation, and that we need to go back and check our answer. So I'll write our formula one more time at the top, P1, V1, P2, and then we're solving for V2. So then it kind of becomes an algebra problem where we take each of our variables, plug them in to the correct spot, and then we'll solve. Okay, so a little bit of an algebra reminder here. When you are solving for a variable, you want to try to isolate it by itself. And so what that means is to solve for V2, we need to get it by itself. Since it's being multiplied by 760, we're going to do the opposite and divide both sides by 760. Okay, so then into my calculator, I plug in 740 times 2 divided by 760. And so in this case, this tells me that my second volume is 1.95 liters. And that's rounded off to the same number of significant figures as the other volume is. So 3 sig figs will keep 3 sig figs as well. And so that matched our prediction. The volume did decrease from 2 liters to 1.95 liters. So it looks good, and so we'll circle this as our final answer. All right, so let's go to the next problem and see what we can do there. So we'll start with the same approach and just try to figure out which of our variables we're going to be using. We have 4.40 liters, that's a volume, is collected at 50 degrees Celsius. That's a temperature. What will be its volume upon cooling to 25 degrees Celsius? So in this case, it looks like we're using volume and temperature, which will be Charles's law, and that pressure is being held constant. So this will generate my formula, V1 over T1 equals V2 over T2. So now that we've got our formula, let's go ahead and list out our variables. V1 and T1 for our starting conditions, V2 and T2 for our ending conditions. Our starting volume is 4.40 liters, and our starting temperature is 50 degrees Celsius. They're wanting us to solve for the new volume after we cool it to 25 degrees Celsius. So there's 2 things we need to do before we're ready to plug in. The first being that anytime you're given a temperature in Celsius, we need to go ahead and convert it to Kelvin by adding 273.15. So we'll go ahead and do that to both temperatures. So in your calculator, 50 plus 273.15, that gets you 323.15 Kelvin. And then the bottom one, 25 plus 273.15 gets you 298.15 Kelvin. All right. Second, we also want to go ahead and make our prediction. What we see happening is a cooling process. So that means the temperature is going down. Since volume and temperature are directly proportional, if temperature goes down, so should volume. So our prediction is that our volume should decrease from 4.40 liters. All right, now with our work in mind, we're ready to actually set up our problem. So we have V1 over T1. We're solving for V2 as it's placed over T2. So let's fill in the values that we know. 4.40 liters over 323.15 Kelvin. We don't know V2, and that's placed over 298.15 Kelvin. All right. So at this point, you're welcome to kind of solve it like you normally would in algebra, but I'll go ahead and show you another technique that oftentimes students like to use, which is cross-multiplying. So if you have 2 fractions set equal to each other, what you can do is multiply the denominator of the right side by the numerator of the left side. So that would be 4.40 times 298.15. And then what you can do is set that equal to the other 2 parts multiplied. So you take the denominator of the first side, 323.15, and multiply it by the numerator of the second side, V2. Then this becomes a problem just like before, where we divide by the variable next to the V2. That way we can isolate it by itself. Then if we plug into our calculator, 4.40 times 298.15 divided by 323.15. And oops, hit the wrong key at the end there. One moment. There we go. And so that's telling us that our second volume will be 4.06 liters. And so we did have a decrease, just as our prediction. It looks like we're on the right track, so we'll go ahead and box that in as our final answer. And for my basketball players out there, if you've ever wondered, well, hey, why does my basketball kind of seem a little less bouncy, on maybe cold days in the winter as opposed to warm days in the summer? What happens when those gas particles inside your basketball kind of cool off is they take up kind of less volume and they also exert, less pressure. And so your ball seems to be a little flat. So kind of neat. All right. So next to last problem here. So again, same approach. Let's figure out which variables we're using and then move on from there. So this one tells me I have a constant volume with a pressure of 0.350 atmospheres at 50 degrees Celsius, which is a temperature. Then it says, what is the pressure when the temperature is doubled? So this was nice. They go ahead and tell me that the volume was constant, so I'll just be dealing with pressure and temperature, which is Gay-Lussac's law. So that should be P1 over T1 equals P2 over T2. So now what I'll do is I'll go ahead and make a list of my variables. We'll fill in the list and then we'll be able to solve and plug into our equation. All right, so I'm starting out at a pressure of 0.350 atmospheres and I have a temperature of 50 degrees Celsius. Okay, then it says, what is the pressure when the temperature is doubled? So we're trying to solve for the pressure and we're pretending as if the temperature is doubled. But they give us a hint that says, remember to convert to Kelvin before doubling. So what we'll need to do is go ahead and convert our first temperature to Kelvin by adding 273.15. And so when you do that, you should get 323.15 Kelvin. And then we say, okay, well, what happens if we double that? So we'll multiply 323.15 times 2 to get 646.3 Kelvin for our second temperature. All right, so let's go ahead and make a prediction right quick. What we see happening is the temperature is increasing. Since pressure and temperature are directly proportional, if temperature goes up, so should pressure. And that's because the faster those molecules move, they'll create more force kind of on the walls of their container by colliding more often. All right, now let's go ahead and set up our problem and work it out. So we've got P1 over T1 equals P2 over T2. Our first pressure was 0.350, first temperature 323.15. We're looking for the second pressure, and then we know the second temperature is 646.3. So again, let's go ahead and do our cross multiplication. 0.350 times 646.3, and we'll set that equal to 323.15 times P2. All right. Then again, it becomes more clear as to what we need to do to solve. So we'll divide both sides by the 323.15, and then we'll go ahead and solve out. So 0.350 times 646.3 divided by 323.15. And that gets us for P2. That tells us that it's 0.7. And we'll go ahead and add 2 zeros to make it 3 sig figs, just like the other pressure, to get 0.700 atmospheres. And so we check our prediction and ask ourselves, did that second pressure, actually go up as we predicted? It did, so it looks like we're good to go with this as our final answer. All right, so now just one more example. Thank y'all for hanging in there. So let's go back up to the top right quick and work that last I do problem. And we'll talk about what makes it a little different than the other 3 problems that we've worked. So again, we'll kind of approach it the same way, PV over T. So here they say 2 liters of gas, that's a volume, is collected at 25 degrees Celsius, that's a temperature, and 745 millimeters of mercury. Wow, that's the pressure. So what's happening here is this is actually going to use the entire combined gas law to work the problem because we're dealing with a pressure, volume, and temperature. So our equation for this will be P1 V1 over T1 equals P2 V2 over T2. All right. And so again, we've been using the combined gas law as the starting point for each of these problems. We just haven't had to use, every variable yet. So let's go ahead and kind of make our list. So we'll need a P1, V1, T1, and then we'll need a P2, V2, T2. All right, so first pressure is 745 millimeters of mercury. The first volume is 2 liters, and the first temperature is 25 degrees Celsius. Then they ask us, what is the volume? So we're going to be solving for the new volume at STP. Now what STP stands for is standard temperature and pressure. And so that has a set pressure value of 1 atmosphere and a set temperature value of 0 degrees Celsius or 273.15 Kelvin. And since we're going to have to convert to Kelvin anyways, let's just take what they've given us and use the Kelvin from the start. All right, so now a few things we need to do before we're ready to solve. So one, let's go ahead and convert that first temperature into Kelvin by adding 273.15. So we'll do 25 plus 273.15 gives you 298.15 Kelvin. All right. Now, here's another thing I'd like to point out. If you notice, our second pressure is in atmospheres, but our first pressure is in millimeters of mercury. All right. And so on your blue reference sheet, there's actually a special relationship between these 2 variables. And what it tells us is that 1 atmosphere is equal to 760 millimeters of mercury. Okay. And so what needs to happen is we need to have both of those kind of in the same unit before we solve. So instead of plugging in 1 atmosphere for the second pressure, we're going to use 760 millimeters of mercury. Okay. And if you don't have your blue sheet handy, you may want to write that down, that 760 millimeters of mercury is equal to 1 atmosphere. All right. And so that means like half an atmosphere would be equal to half of those millimeters of mercury. All right, so now we've got that settled, I think we are ready to begin. So we've got our whole formula, P1 V1 over T1 is equal to P2 V2 over T2. So let's plug in our first pressure, 745 millimeters of mercury, our first volume, 2, and our first temperature, again, remember to use the Kelvin temperature, 298.15. Then we'll plug in our second values after the change, 760 millimeters of mercury. Our second volume is what we're solving for. Then our second temperature is 273.15 Kelvin. Okay, again, we'll go ahead and do our cross multiplication. So we'll take 745 times 2 times 273.15, and we'll set that equal to the other sides cross multiplied, 298.15 times 760 times V2. All right, then to get V2 by itself, we'll divide both sides by 298.15 being multiplied by the 760. Okay, then we'll have some fun with our calculator, right? And again, please make sure you're trying to plug these in, because it's always good to stay in practice on your calculator use. All right, so let's see what we get. So 745 times 2 times 273.15, then divided by 298.15 divided by 760. All right, and so that's getting us 1.80 liters. Here we go. All right. And so if you're not getting 1.80 liters, what probably happened is you may not have divided by both of these things. So make sure, like if you're using your calculator, that you either, like before you hit the divide by sign, or sorry, after you hit the divide by sign, that you make sure you're dividing by 298.15 times 760. So both of those numbers should be going kind of in the denominator because you're dividing by, both of them. All right. Okay. And I think that gets us. So now that just leaves you guys kind of opportunity to get this really kind of firmed up by practicing some more. So thank you so much for watching, and hope you have a great day.